Alright, so this will be the structure of our neural network. There will be an X layer, which is the input layer, and it has 6 features, right? So we have feature x0, x1, x2 up to x5, right? So let's name it as x1, not x2. This was a typo from my side, I'm sorry for that. Okay, so we have x0, x1 up to x5, and also we have w0, weight 0, w1, w up to w5. For the sake of simplicity, we are not adding bias into it, just for the just because we want to write a very simple implementation over here. Later on, when we'll be working on a project, we'll write we'll make use of bias as well, right? So this is the simplest neural network that we have. So first of all, we will compute the forward feed forward thing, then it will give us y hat, right? And we already have y, we will minus it with y, and then this term will be multiplied with x. What is x? X is this thing, and it will give us the and then we will take sigmoid derivative of it, and then it will give us the updated value of w0, w1 up to w5, and that thing will be called as back propagation. Then again we'll do some feed forward for next axes or for next number of features, and so on, right? Okay, so let's go on implementation. So here we'll say define, let's say neural network, let's say define NN. And here it will receive features, here it will receive targets, it will receive number of epochs, which is by default, let's say 1000, and it will receive a learning rate, which is, let's say by default it will be 0.0001, right? So let me repeat, these two things are hyperparameters. You can play around with these things. Great. Now the next thing is we want to generate a seed. So here we'll say random dot seed, let's say 42, right? We have done it in logistic regression implementation as well, so I'm not going to repeat it over here, that what it is doing. Okay, so here we'll receive number of records and number of features. And how can we get it? We can get it by saying features dot shape, right? Okay, the next thing is we will be initializing the weights. And how many weights do we need? So first of all, we need we'll initialize with some random values, and these random values will be normally distributed, and the size of this vector would be, what would be the size? Size would be the number of features, right? So how many weights do we need? It depends upon how many number of features do we have, right? So here we have, it says that we have 5 number of features. Actually we have 6 number of features, since we are starting it from index 0, that's why it is x5. So we need 6 weights from w0 to w5, right? So we need feature many weights, right? Okay, great. Next thing is, so we are going to write a loop for every epoch. So we'll say for epoch in range epochs, and here we'll say delta w or change in w, it's the same thing. So numpy dot zeros. So here we are just creating a vector of zeros, and its shape would be exactly as the shape of weights, right? So that we can compute the change. Okay, so the next thing is we are going to loop over every feature, right? We have 360 features in we have 360 rows in our training data set, right? So we are going to loop over every feature or every row, not every feature but every row. So we'll say x comma y. We know that x denotes feature and y denotes target. So how can we do that? We'll say zip. We will zip the feature dot values, and we also have targets with us. Great, we'll zip them. So here we have x and y. At a time, x and y will represent one row, right? So first of all, we'll get some output, or you can say not output, let's call it y hat, right? So how can we get y hat? So we'll say sigmoid of numpy dot product of what? Of x and weights, right? And then we will create we will compute the error term, and error term would be computed from the error formula that we have, error term formula that we have written. And here we'll pass x, y, and y. What do we need to pass? X and y hat and y. So here we'll pass x, y hat, and then y, right? So x will be the features, y hat will be the output or prediction, and y will be the original label. And then simply what it will do is we'll say delta w plus equals to error term, right? And then what do we want to do? Then we want to update the weights after every you can say every run over the whole number of training features, number of training records, right? So let's say this whole loop will be done. When this whole loop will be done, it will be iterated over the whole training set. Then we will have a delta w, right? And then here we'll say weights plus equals to learning rate multiply by delta w. That's it. And yeah, that's it. So here we are doing forward propagation, here we are computing the error, and here we are updating the weights. So these three things are called back propagation. By the way, it's not that simple. Since we are dealing with just one neuron, that's why it looks very simple, right? So, and when we'll be working with deep neural networks, it will be not very difficult, but it will neither be this simple, right? Okay, so now just for the printing some statements, for the sake of printing some statements, here we'll say for epochs, so we want to print results after, let's say, every 10% of iterations, and we'll say out equals to, so yeah, so here we'll say sigmoid of numpy dot product of features and weight, right? Weights. And then we'll say loss equals to, here we are just computing the loss, so we'll say numpy dot mean, we are computing the average loss, so here we'll say error formula, and in this formula we'll say targets, targets and the output. Great, looks fine. So here we'll print epoch, so it's epoch number e, and then we'll say print the training loss, which will be loss that we have computed over here. And then nothing, then just we'll be printing some lines to discriminate that the one printing statement is done, right? So yeah, we are done. And finally this function will return the weights. Great. And here what we are going to do, we are going to say weights equals to neural network function, and in neural network function that we have created over here, we have to pass features, targets, and that's it. Epochs and number of epochs and learning rate is already there, so we'll say features and targets. That's it. So let's run it. Oh, it is giving us an error. It says that E is not defined. Where have we used? Okay, here. Oh, so why does I think this should be inside the loop, and this is epoch. Yeah, let's run it now. Again, it gives us an error. It says again E. Oh, now E is here as well, so here we'll say epoch. Run it. Great. So at epoch 0 our error was 0.9, or you can say training loss was 0.9, and then it kept increasing. Why? I think we have done something wrong over here. Let me see. So yeah, it looks like our error term formula is not correctly written, because it should not be y hat minus y, it should be y minus y hat, because we want to deduct the output from the original target, right? So now it should work fine. Let's run it again. So yeah, so previously the error loss was 0.9, the training loss was 0.9, then it reduced to 0.6, then 0.61, and so on and so forth. Yeah, you can see that the loss is not reducing significantly. It is not taking big steps. It just took one big step here, and then it stopped taking big steps. So let's change our learning rate, and let's reduce our learning rate to 0.01, and let's run it again. So yeah, much better now. So it is now the training error is 0.57. So that's how we can implement, or we can train our neural network with just one layer, with just one neuron, right? In upcoming lecture we are going to write the testing code for this neural network. Let's do some testing as well. This training returns us weights, the updated weights, the trained weights, the well-trained weights, right? So we are going to use these weights, updated weights, and we are going to test the model. So let's say test output equals to, we'll say sigmoid, and here we'll say numpy dot, and here we'll pass the features, but the testing features. What was the name of that variable? I forgot. Where is it? Yeah, test features. Yeah, so let's write test features comma weights. These are the updated weights, right? So it will return, it will give us some outputs, and then we'll say predictions equals to test out if how many of these are greater than, so it will store true for those values which are greater than 0.5 and false for those values which are less than 0.5. And then we'll say accuracy, right? Accuracy equals to numpy dot mean, and here we'll say predictions equals to target test, right? So here in targets test we have our labels for the testing set, and then here we are going to just print the accuracy. So accuracy, yeah, accuracy colon, and here we are going to say, we are going to just print the accuracy. Great, let's run it. So our accuracy is 0.625, which means 62%, which is not very good, right? Which means that, so and also we can see that our training loss and our accuracy are quite similar. what do we want to do? So what are the faults? I mean, 62% accuracy on testing set is not a good accuracy. So what are the faults in this data set we are going to study? So not in data set, in this neural network we are going to study that. Moreover, you can change these two parameters and the accuracy will change to some extent, but it will not change a lot. In this case, I've done that, by the way, I've tested it, so it will not change a lot. One of the reasons is, since our data set was too complex to classify, right? So we have used just one neuron. We should have used more neurons. Perhaps we should use more layers as well, right? So we are going to analyze the performance of this neural network, and we are going to see that how can we improve and what are the factors that can improve a neural network that is not performing well. So from upcoming lectures we are going to talk about optimizations.